Okay, this video is going to cover Chapter 4 of Geometry, and specifically Section 4.3 through 4.7. So by the end of this video, you should know how to find the midpoint between 2 points, the slope of a line, the different forms an equation can take, and what geometric probability is. So we'll start off with midpoint and slope conjectures. So our first conjecture, the coordinate midpoint conjecture, states that if x1, y1, and x2, y2 are the coordinates of the endpoints of a segment, then the coordinates of the midpoint are x1 plus x2 over 2 and y1 plus y2 over 2. So essentially, this right here and here is our formula for finding the coordinates of the midpoint. Okay, so now let's do a practice problem with midpoints. So we have point A here at 1, 1, and we have point B here at 5, 3. So A is 1, 1, and B is 5, 3. Okay, so now we know that this is going to be x1, this is going to be y1, and this is going to be x2 and y2. So first we want to find the x-coordinate of the midpoint, and that we do that by adding x1 plus x2 over 2. So that'll be 1 plus 5 over 2, which equals 3. And then now we want to find the y-coordinate. y1 plus y2 over 2, that'll be 1 plus 3 over 2, which equals 2. So now we know that the midpoint is at 3, 2, which we can see here looks just about right. The slope of a line is a really important vocab term to know. It is the incline or steepness of a line, and we measure it by a nice little phrase, rise over run. So essentially what that is it's the change in y, so that's the rise, over the change in x, which is the run. So now we have another conjecture, the slope of a line conjecture, which says that the slope, or m, which is the variable we use for slope, of a line or segment through point 1 and point 2 with coordinates x1, y1, and x2, y2, where x1 is not equal to x2, is this. M equals y2 minus y1 over x2 minus x1, and that's going to be our equation for finding slope. And as you can see, here we're finding the change in y, and here we're finding the change in x. So essentially it is rise over run. So while this equation will work for essentially all lines, horizontal lines and vertical lines have some special rules about their slopes. So the slope of a horizontal line, such as this, as you can see, there's going to be 0 rise ever. So no matter how much run there is, it's always going to be 0 divided by a number. So the end result is going to be 0. So the slope of a horizontal line is always going to be 0. So instead, the slope of a vertical line has no run. So the run is always going to be 0, and the rise is going to be essentially infinite. But it's going to be a problem where you have to divide by 0. So therefore, the slope of a vertical line is going to be what we call undefined, because you can't divide by 0. Okay, so now if we do a slope practice problem, we have point A here, and then point B here. So this is 1, 2, and this is 5, 4. And then we have this line right here. Then what is going to be the slope of that segment? So one way we can do this is we can make a little dotted line here for the rise, so that's going to be 2, and a dotted line here for the run, which is going to be 4. We can just count boxes essentially, and then it's going to be rise over run. So that simplifies to 1/2. But it's not always going to be that simple, so it's really good to know how to use our formula. So our formula says y2 minus y1 over x2 minus x1. So if we say that the first point here is x1, y1, and the second one is x2, y2, then it's going to be, when we plug it into our formula, it's going to be 4 minus 2 over 5 minus 1. And as you can see, this simplifies to the same thing, obviously, but it's really good to know how to use that formula. So now 4.4, we're going to have some conjectures about parallel and perpendicular lines. So the parallel slope conjecture states that in a coordinate plane, two distinct lines are parallel if and only if their slopes are equal. So in this graph, say we have a line here and a line down here. And so we can figure out the slope here. The rise is going to be 1 whenever the run is 2, so the slope is 1/2. And these two lines look parallel, but to check, we have to measure the slope of the second one. So here we can also see that the rise is 1 when the run is 2. So they have the same slope and they're parallel. Now, perpendicular slopes, however, in a coordinate plane, two non-vertical lines are perpendicular if and only if their slopes are opposite inverses. So if you don't know, an opposite inverse is the opposite of a number, so the negative of a number, and then the inverse, which means that, say you have 5/4, the inverse is going to be 4/5. So for this line here, with a slope of 1/2, the opposite inverse is going to be -2, because we both made it negative and we also flipped it over, because 2 is the same as 2 over 1. So if we were to draw that, that would look something like this. And that is going to form a right angle with these lines because it's perpendicular. A quick vocab term, bearing, is an angle measured clockwise from north. So, say on a compass, north is facing this way, and then to measure this angle, the bearing would be measured clockwise. So instead of measuring here, as you might think, you would measure around this way. So this bearing might be approximately 240 degrees. So here we have 3 equations, and you might look at these and think that they're 3 separate different equations, but in reality they're actually 3 different forms of the exact same equation, which means that if we were to fiddle around with them a little bit, we could transform them into the exact same form. So this first one is in point slope form, because we have points here and the slope here. The second one is in slope intercept form, because we have the slope here and we have actually the y-intercept here, which we'll talk about more later. And then this is in standard form, because there are no fractions in the coefficients of the variables. So the standard equations for each of these forms is, so for this one we have y minus y1, which is the point that we're measuring, and then m for slope, and then x minus x1. So the x1 and the y1 are to substitute in for a point. Okay, then for slope-intercept form, the standard equation for that is y equals mx plus b. So again, m is for slope, and then b is for the intercept. Okay, so now we're going to do an example where we're also going to practice transforming point-slope form into slope-intercept form. So here it says, write an equation for the line that passes through the point 2, 2 and has a slope of 3 over 2, and then transform it to slope-intercept form. So, okay, what we know here is enough for point-slope form. So we have our x1 and our y1 here. So we can have y minus 2 equals 3 over 2, which is our slope, times x minus 2. And then to transform this to slope-intercept form, first we need to distribute here. So then we have y minus 2 equals 3 halves x minus, and then this actually cancels, but we have negative 3. And then we can move this 2 over, so we have y equals 3 halves x minus 1, because that was negative 3, and then we added 2 to both sides. And then this is our slope-intercept form. Okay, so this might seem a little redundant, but so the y-intercept, some vocab, is the point at which a line crosses the y-axis. And so this is very similar to the x-intercept, which is the same thing except for the line crosses the x-axis. So we have a conjecture, the slope-intercept conjecture, which we've kind of already covered. If the graph of a line has a slope of m and a y-intercept of 0b, then the equation of the line can be written in the form y equals mx plus b. So it should give you some idea about how important this is, that it has its own conjecture. Okay, so 4.6 is about finding intersections of lines, and so there are two approaches. So the first approach is graphing. So here we have two equations, and to find the intersection of them, we're going to graph both of them. So the first one, we can see that the y-intercept is going to be negative 5 because it's in slope-intercept form. So that's going to be down here. And then the slope is going to be 3. So that's up 3 and then over 1. So here we can graph that. Just like that. And then for the second line, it's in standard form. So what we're going to do, there's a trick where if you plug in 0 for y, so then that'll make this term 0, and you just have 4x equals 12, and you can simplify that to x equals 3. That's going to be the x-intercept because we plugged in 0 for y, and then we can do the same thing with x. So say x is 0, we're just going to have 3y equals 12, or negative 3y equals 12, so that's y equals negative 4, and that's the y-intercept. So then we can plot both of those points, and that will give us just enough to make the line. So as you can see, this doesn't actually always work out. We can see where they intersect, but it's going to be very difficult to actually find a point there. So that's why we have our second method, which is setting the equations equal to each other. So in our second approach, we're going to do some algebra. we're going to substitute in the y here for what y equals here. So we're going to have negative 3 times 3x minus 5 plus 4x equals 12. And then we can solve for x. So we're going to have negative 9x plus 15 plus 4x equals 12. And then we can combine like terms. Negative 5x plus 15 equals 12. We can subtract 15 from both sides to get negative 5x equals negative 3. And then as we can see, x is going to equal 3 over 5. And then we can plug this back into our original equation and see what y equals. Okay, so then this is going to be 9 over 5 minus 5. And instead of the 5, we can put 25 over 5, which is the same thing. And then we can subtract fractions, and that will equal negative 16 over 5. So then we have our x and our y. So the point of intersection is going to be this. And obviously that would have been very difficult to find on a graph. So this is a really interesting conjecture to know. It's called the centroid coordinates conjecture. And it says that if triangle MNO has the coordinates M is AD, N is BE, and O is CF, then the centroid, which we covered in an earlier chapter, has the coordinates A plus B plus C over 3, and D plus E plus F over 3. So essentially, the centroid, the point of the centroid, is going to be the average of all the endpoints of the triangle. So say the centroid is around here, it's going to be the average of these 3 points. So geometric probability. Probability is, in essence, the number of successful outcomes over the number of possible outcomes. So it's what you're looking for over everything that's possible. So here we have an example problem. Given line AB, or segment AB, with midpoint M, what is the probability of randomly selecting a point on the segment closer to point M than to point A? So essentially, everything on this side of the line is going to be closer to M than to point A. So that already gives us a 1/2 or 50% probability of choosing a point that's closer to point M than to point A. So dealing with this side, however, we can actually just split it in half, because everything here is going to be closer to point M, and this is the small portion that's going to be closer to A than M. So if we add all these up, then we have a 1/4 probability of selecting something closer to point A than M, and we have a 1/4 plus 1/2 probability of choosing something closer to point M. So that's going to add up to 3/4, or a 75% chance of choosing something closer to M than A.